Okay, we did tropical forcing of the extratropics, extratropical forcing of the tropics in terms of the theories and mechanisms that have been discussed so far in literature. Let's conclude this part by looking at observations and mechanisms of the coupling between the tropical extratropical interactions. We have already implied this with this kind of a figure we looked at before, where we said the winter surge here, the so-called surges during winter, which are related to this blocking pattern. So here we are looking at the MJOs that cross the maritime continent and the MJOs that do not cross the maritime continent. But here we are looking at several days. So day 0, day -3, day -2, day -1, day 0, day 1, and day 2. So day 0 denotes the day when the cold surges are the strongest. I hope I said that correctly before as well. But you can see as day -3 to day -2, -1 and 0, the extent of the blocking pattern here and the pressure anomalies here are evolving, and they almost get connected here. So -3, -2, -1 and 0. This is when the winter surges, cold surges are the strongest, and that affects the convection or the maritime continent and facilitates the transition across the maritime continent. And then as it goes further east, there is a feedback to the higher latitudes. There is also a nice paper by Krishnan showing that the break periods over the Indian monsoon region during the boreal summer have a feedback with the mid-latitude surges, which results in a water vapor feedback that actually extends and persists the break period. So they look at several years of case studies and propose a mechanism of how this tropical extratropical forcing of the break period and then the feedback to the extratropics works, or the coupling works during a monsoon season in terms of the break periods and their persistence and duration. Okay, this is looking at the evolution of the 200 hectopascal velocity potential in 8 MJO phases based on 30 northern winters between 1979 to 1980 and 2008-2009, and pentad data derived from daily averaged and Sepencar reanalysis product. So you can see going from phase 1, 2, 3, 4, 5, 6, 7, 8, you have the opposite phases of the velocity potential in the upper atmosphere propagating eastward here. So you can see the clear eastward propagation of the MJO and the associated upper level velocity potential associated with that. So the idea of this section, of course, is to look at theoretical explanations for this. The papers by Fredrickson and Lynn, Fredrickson and Fredrickson and Fredrickson and so on have produced lots of these theories, including what kind of instabilities are critical for the extratropical forcing of the tropics and the feedback. So the idea here is to compare to the observations and at 300 hectopascal. They use typically a 2-layer linear model with 3D background state, which affects, of course, the teleconnections, as we saw already. This is the evolution of 300 hectopascal velocity potential at 8 MJO phases for the leading theoretical interseasonal model for the basic state that include cumulus heating in the deep tropics, which is needed to generate the waves, and evaporation wind feedbacks. So that's kind of the main processes this model argues for in terms of reproducing the observed velocity potential propagation with the MJO phases. Okay. This is showing the extratropical signature of the same thing. Extratropical northern hemisphere 300 hectopascal stream function anomalies for reanalysis data as shown in figure 7. So corresponding to this figure, we are looking at the extratropical signatures for basic state that include cumulus and evaporation wind feedbacks. Oops. Sorry, here. Anomalies for reanalysis data, MJO phases 3, 4, and 3, 4, and 5 are shown. So obviously, in the tropics, we are looking at all phases, and with the lag, there is a relation, lag or lead, there is a relation with the mid-latitude flow features. So we are looking at the North Pole, and North America is here, so that's the Pacific sector, Atlantic sector, and the Asian landmass. Clearly there is low latitude, high latitude connections that are coherent with the MJO phases in terms of upper level velocity potentials and stream functions at mid latitudes. So as we saw before, the certain phases of the MJO convection is enhanced by mid-latitude influence, and that enhanced convection produces Rossby waves, which then go back to the mid-latitudes and affect the flow features. So clearly there is a coupling. This is similar to the previous figure for the leading theoretical intraseasonal mode for evap basic state. So evaporative wind feedbacks are allowed, and the mid-latitude tropical connections are again manifest in the same MJO phases of 3, 4, and 5. So obviously we always have observations, and we build a hypothesis, and we try to get more data to test the hypothesis, and if the hypothesis is confirmed, then we propose a theory, and then you try to build a model which can test the theory. So this Fredrickson and his collaborators have over time built a lot of studies of these instability models that address the tropical, extratropical interactions and coupling. Okay, so this is just kind of adding to the details of the interseasonal variability and theories that we are focused on in these series of podcasts. It's pretty clear that the interseasonal variability in the tropics is very closely connected and feeds back to the extratropical forcings. The key question, of course, is whether the time scale selection of the interseasonal period itself is related to extratropical forcing, or if it's independent. And there are papers which try to look at this by shutting off the extratropical links, and also looking at various processes, whether you need convection or other instabilities like vertical shear in the tropics to generate the timescales and the processes that we observe. Obviously, there is no consensus yet as to exactly how the scale selections happen. There are open questions of, for example, the role of the ocean and sea surface temperatures. We mentioned that when the ocean and atmosphere models are coupled, MJOs do seem to improve in terms of amplitudes, and SSTs always have a strong link to the convection in the deep tropics, and SSTs vary longitudinally, and that is associated with the moving heat source of the MJO. But the scale of the SSTs tend to be SST anomalies associated with MJOs tend to be an order or two magnitude smaller than the planetary scale of the MJOs. So how does that coupling happen? There is one study by Zolay that says that when the wave number, frequency, and dispersion are close to each other in the lower atmosphere and the upper ocean, then the coupling can happen, and the small scale interactions between the SST and the atmosphere can grow into an instability of planetary scale. So lots of pieces of ideas exist, and the main point we would want to leave here is that the tropical extratropical interactions happen, and they are related to the background state and the moving heat source, its location, and so on. But whether one or the other is very critical for selecting the intraseasonal time scale is not yet completely understood.